So back in 1971, there was this, well, I guess you'd call it a pretty dark moment in public health history. The chairman of Philip Morris actually went on national television.
Right. And he deployed what was basically a massive statistical blind spot on the American public.
Exactly. He sat there and confidently stated that smoking during pregnancy wasn't harmful. I mean, he admitted the babies born to smokers were smaller, but he claimed they were, quote, just as healthy.
Which is wild.
Yeah.
And he even went so far as to suggest that, some women might actually prefer having smaller babies.
Yeah, just an unbelievable spin. But the craziest part is how he got away with it statistically at the time.
Because of the natural variance, right. I mean, the immense biological variance in human birth weights meant that smaller medical studies back then, they often just failed to generate the strict statistical significance needed to prove him wrong.
The noise of the data basically obscured the signal of the harm.
Precisely. The math couldn't quite catch up to the reality because of the limits of those specific samples.
And, that is the ultimate danger of raw numbers. We look at a spreadsheet from a scientific study or a corporate report, and we just assume we're looking at objective reality.
We assume it's the whole picture.
Right. But we almost never have the entire population's data. We are always looking at a sample. We're essentially trying to understand the entire landscape of reality by looking through a tiny keyhole.
Which is a really tricky thing to do without the right tools.
So, welcome to today's deep dive. It is April 16th, 2026, and today we are giving you the tools to widen that keyhole. We are diving into Chapter 7 of the Open Intro Statistics 4th edition textbook.
Yeah, specifically, we're dissecting the mechanics of inference for numerical data.
And just a quick heads up for you listening, our mission today isn't to review basic concepts, like we aren't going to re-explain the bell curve or what a null hypothesis is.
Right, we're assuming you already have those foundations down. Our goal today is to explore how statisticians actually manage the inherent messiness of real-world data.
Because those pristine theoretical assumptions, they break down really fast in the real world.
They absolutely do.
We are looking at the toolkit that prevents us from being fooled by small samples. And the sources today give us some phenomenal real-world applications to really tear apart.
Oh, definitely. Everything from tracking heavy metals in the diets of Japanese dolphins to evaluating the actual financial variance between campus bookstores and Amazon.
Okay, let's unpack this. When we are forced to draw sweeping conclusions from an incomplete pile of data, the very first mathematical hurdle we run into is estimating the spread or the standard deviation.
Yeah, that's the core constraint of real-world statistics right there.
Because we never actually have it, do we?
Almost never. I mean, the central limit theorem is this elegant concept assuring us that sample means will distribute normally as we gather more data. But the catch is that the mathematics of the perfect normal distribution require us to know the true standard deviation of the entire population.
Which is impossible in most cases.
Exactly. If we're testing a new blood pressure medication, we obviously don't know the exact variance of blood pressure for every single human being on Earth.
So we're forced to substitute the population's standard deviation with the standard deviation we calculate strictly from our little sample.
Which introduces a huge secondary layer of severe uncertainty.
Right.
When you have a small sample, your estimate of the mean is already pretty wobbly. And by using that same small sample to also estimate the spread, you just compound the uncertainty.
So if you plug that really shaky estimate into the unforgiving formula of a standard normal distribution, what happens?
Well, the math is going to output a false sense of security.
Yeah.
It will literally tell you your results are statistically significant, when in reality they might just be a random artifact of your limited sample.
I always picture it like cartography.
Oh,
Yeah, like if you're drawing a map of a coastline based on incredibly precise satellite data, you can use an ultra-fine point pen. That pen is your perfect normal distribution.
Okay, I see where you're going with this.
But if you're drawing that exact same coastline based entirely on the blurry descriptions of 3 sailors you met in a tavern, you have to use a really thick marker.
Right, because you have to account for the blurriness.
Exactly. The thick marker acknowledges the margin of error. You just can't draw a razor-thin line because you honestly don't know exactly where the coast actually is.
That analogy maps perfectly onto the statistical solution to this exact problem, which is the t-distribution.
The famous student's t-distribution.
Yeah. It serves as that thick marker. It resembles the standard normal distribution. It's still bell-shaped, but the mathematical density is pushed outward from the center.
Creating those thicker tails.
Exactly.
thicker tails.
And those thick tails mathematically force us to widen our confidence intervals. They literally require us to see a much larger effect in our data before we are allowed to declare it statistically significant.
Right, it stops us from jumping to conclusions.
The p-distribution basically acts as a mathematical safety net against our own ignorance. What's fascinating here is how the t-distribution is not a static shape. It's not just one thick marker.
Right, what do you mean?
It dynamically adapts to your specific level of uncertainty through a parameter known as degrees of freedom.
Which is just your sample size minus 1, right?
Simply your sample size minus 1. So when you have a tiny sample, say, just 5 observations, your degrees of freedom are super low.
Just 4.
Right. So the tails of the t-distribution are at their absolute thickest. You're using the thickest marker possible. But as your sample size grows, the degrees of freedom increase, and those thick tails incrementally shrink.
Because your estimate of the population's standard deviation is becoming more accurate with every single new data point. The blurriness of those sailors is fading.
Precisely. By the time your sample size surpasses 30, the t-distribution has essentially morphed entirely into the standard normal distribution.
The safety net retracts because you just don't need it anymore. So let's see this safety net in action with the first major study from Chapter 7. Researchers wanted to understand the mercury concentration in the muscle tissue of Risso's dolphins from the Taiji area in Japan.
A really important environmental study.
But they obviously cannot round up and biopsy every single dolphin in the entire ocean.
No, of course not. They managed to gather a sample of 19 dolphins.
Oh, 19 dolphins.
Right. The sample size of 19 leaves us with 18 degrees of freedom. That places us squarely in the territory where the t-distribution's thick tails are absolutely mandatory.
But wait, before we can even apply that math, the textbook points out the data has to pass 2 strict condition checks, right?
Yes. Independence and normality.
Now, independence is fairly straightforward. The text notes this was a random sample, meaning one dolphin's mercury level doesn't dictate another's.
Correct.
But the normality condition always strikes me as, well, kind of a paradox. Like, how can we possibly verify that the entire population of dolphins has a normally distributed mercury level when we only have 19 scattered data points?
Well, you cannot verify it absolutely. It's impossible, which forces statisticians to rely on rigorous rules of thumb.
Okay, so what's the rule here?
For a sample size under 30, the requirement is to examine your sample data for clear, unambiguous outliers.
Just visual outliers.
Yeah, the t-distribution is robust enough to handle slight skews in the data. But if you have a massive outlier in a tiny sample, it will violently drag the mean and inflate the standard error.
Completely destroying the reliability of the inference.
Exactly.
So looking at the data set for these 19 dolphins, the sample mean was 4.4 micrograms of mercury per wet gram of muscle.
Okay.
The lowest reading in the sample was 1.7 and the highest was 9.2. So that actually means every single observation fell within roughly 2.5 standard deviations of the mean.
Which is great. The absence of extreme outliers in that set allows us to tentatively accept the normality condition and just proceed with the t-distribution.
Yes.
As a crucial side note for larger studies, though, once your sample size exceeds 30, the central limit theorem kicks in so strongly that you really only need to screen for particularly extreme outliers.
Oh, right. The textbook illustrates that relaxed rule brilliantly. It uses Twitter followers.
Yes, the Twitter example.
So, like, if you're sampling Twitter accounts to find the average follower count, and you randomly pull a massive pop star with 10 million followers into your little sample of 50 normal users, that one single observation will completely skew the mathematical reality.
Right. You have to isolate those extreme outliers regardless of how big the sample size is.
But getting back to our dolphins, we passed the checks. So the researchers calculate the standard error, they apply the t-distribution with 18 degrees of freedom, and they generate a 95% confidence interval.
And the resulting interval spans from 3.29 to 5.51 micrograms per wet gram.
Okay, so what does that tell us?
This gives us mathematical justification to state that we are 95% confident the true average mercury level for the entire population of these dolphins falls within that window.
And for you listening, the biological implications of those numbers are just staggering.
They really are.
The textbook notes that in some regions, a mercury level of 0.4 is considered the threshold for severe toxicity, 0.4.
And our lower bound is what?
Our lower bound, literally the absolute best case scenario based on our 95% confidence, is 3.29.
Wow.
Yeah. By using the t-distribution to properly manage the uncertainty of a small sample, the researchers didn't just find a data point. They proved a systemic, catastrophic environmental failure that poses a massive health risk to anything consuming that meat.
It perfectly demonstrates how confidence intervals provide this reliable landscape of reality.
Yeah.
We don't have the exact number, but we have a highly defensible boundary.
Right.
However, simply establishing a boundary isn't always the goal. Often, we're tasked with directly interrogating a specific historical claim or an assumed truth.
Which transitions us perfectly from building confidence intervals to conducting rigorous hypothesis testing.
Yes, moving from exploring to testing.
The textbook grounds this concept in the Washington, D.C. Cherry Blossom 10-mile race.
A classic dataset.
Yeah, so the historical baseline is established for us. In 2006, the average finish time for all runners was 93.29 minutes.
Okay, so that 93.29 is our fixed point of comparison, our null hypothesis. And the research question is whether the overall population of runners is getting slower as the years progress.
Right. To test this, researchers pulled a random sample of 100 runners from the 2017 race. The average finish time for that specific sample was 97.32 minutes.
So they were slower.
Well, obviously 97 is a larger number than 93, but the real statistical challenge is determining whether that gap of roughly 4 minutes is a permanent shift in the entire runner population, or if the researchers simply stumbled upon 100 people having a really sluggish morning.
Exactly. And we approach this by calculating the standard error of our 2017 sample.
Which tells us what?
It tells us how wildly we expect sample means to fluctuate purely by chance. For these 100 runners, the standard error was calculated at 1.70 minutes.
Okay, so we then map that standard error onto our observed difference to generate a t-score.
Let's walk through that math.
Sure. We take the 2017 sample average of 97.32, we subtract the 2006 baseline of 93.29, and we divide that difference by our standard error of 1.7.
And that gives us?
The resulting t-score is 2.37. So what does this all mean? We have a score of 2.37. How does that translate into a definitive answer about the runners?
Well, the t-score measures the distance between our sample data and the null hypothesis, but it measures it in units of standard error.
Ah, okay.
So a score of 2.37 means our 2017 sample mean is nearly 2.5 standard errors away from the 2006 baseline.
This was pretty far.
It is. When we map that specific distance onto the t-distribution using 99 degrees of freedom, by the way, since our sample size is 100, we extract a p-value of 0.02.
That 0.02 is the probability of seeing a sample of runners this slow if the true overall population was still actually running at that brisk 2006 pace.
Exactly. It is nearly a 2% chance.
Operating under the standard significance threshold of 0.05, that 2% probability is low enough that we are mathematically obligated to reject the assumption that nothing has changed.
The evidence firmly supports the alternative hypothesis.
Yeah.
The true average finish time for the runners has objectively increased. They are slower.
We took a massive data set of chaotic, highly variable race times, applied the t-distribution, and extracted an undeniable demographic trend.
Which is powerful.
It really is. But that methodology relies on comparing a single group's average to a static baseline.
Right.
What happens when the massive variation within the group itself threatens to drown out the very signal we are trying to measure, like when the data is just too noisy?
That specific analytical nightmare is exactly why statisticians utilize paired data.
The UCLA textbook study is the perfect illustration of this.
Oh, the Amazon versus campus bookstore debate?
Exactly. The textbook provides a data set of 201 courses at UCLA. Out of those, 68 courses had required textbooks that were available simultaneously at the official UCLA campus bookstore and on Amazon.
Okay, so we have 68 books with 2 prices each.
Right, and the objective is to determine if Amazon's prices are actually lower.
Now, if a junior analyst were handed this data set, their very first instinct might be to just calculate the average price of the 68 books at the campus store, calculate the average of the 68 books on Amazon, and simply run a t-test on those 2 independent averages.
But that approach would completely sabotage the analysis, wouldn't it?
Oh, absolutely.
Because if you look at the raw data, one course might require a highly specialized medical textbook costing $250, while another course requires a classic literature paperback costing like $9.
Right.
If you just average all 68 books together, the sheer financial variance between the medical text and the paperback creates a massive standard error.
It creates huge noise.
Yeah, that bloated standard error acts like static on a radio, completely drowning out the subtle differences in price between the 2 retailers.
So the solution here is to link the observations. The $250 medical book at UCLA has a direct one-to-one relationship with the $250 medical book on Amazon.
It's the exact same book.
Exactly. By subtracting the Amazon price from the UCLA price for each specific title, we instantly eliminate the variance caused by the nature of the books themselves.
We distill two messy columns of prices into a single, incredibly clean column of 68 individual price differences.
We are no longer studying the cost of textbooks at all. We are exclusively studying the retailer markup.
I love how elegant that is. So running the numbers on that column of differences, the mean difference is $3.58. The standard deviation of those differences is $13.42.
And calculating the standard error and generating the t-score gives us a p-value of 0.0312.
Which safely clears the standard 0.05 threshold. The null hypothesis is rejected, and we can state with statistical backing that Amazon is, on average, cheaper.
The math doesn't lie.
But as someone looking really closely at the source material, I have to inject a crucial layer of critical thinking here.
Please do.
The textbook explicitly warns us against confusing statistical significance with practical, real-world utility.
Ah, yes. The math proves Amazon is cheaper, but it doesn't necessarily dictate consumer behavior.
Right. Take a close look at the histogram of those 68 price differences provided in the text. It is not just a uniform block of savings.
Not at all.
While there are a few extreme outliers where Amazon saves you $30 or $40, a massive cluster of the data sits right around the zero mark. In many instances, the UCLA bookstore is actually cheaper, or the difference is literally pennies.
That's a great point.
If a textbook is only $1.50 cheaper on Amazon, the immediate convenience of just walking across campus and acquiring the book instantly might totally obliterate the statistical advantage of waiting 3 days for shipping.
That distinction right there separates mere data entry from actual data analysis. The p-value tells you the trend is mathematically real, but the histogram tells you how to actually apply that reality in life.
Exactly.
Which provides a seamless transition into the final and really the most structurally complex scenario covered in Chapter 7, which is evaluating unpaired means.
Right. We've handled single samples, and we've neutralized variance using paired data. Unpaired means represent the scenario where we have two completely independent groups with no one-to-one relationship to connect them.
Like the sheep study.
Yeah, the textbook briefly highlights a veterinary study on sheep suffering from heart attacks. 9 sheep were randomly assigned to receive embryonic stem cells, and 9 received a placebo.
And the results there were incredibly clean. The stem cell group demonstrated a 7.83% greater improvement in the heart's pumping capacity.
Which is huge.
Yeah, and factoring in the variance, the 95% confidence interval showed the true improvement was somewhere between 3.32% and 12.34%.
A resounding success. Even with a microscopic sample size of just 9 sheep per group, the medical effect of the stem cells was so powerful that it easily punched right through the statistical noise.
It was a massive signal.
But that clean result really just sets the stage for a much darker data set. Here's where it gets really interesting. The text shifts to a study tracking 150 births in North Carolina over a year. The researchers divided the data into 2 independent groups. They took the newborn weights of 50 mothers who smoked during pregnancy and compared them against 100 mothers who did not smoke.
And the baseline calculation there shows a pretty stark reality. The babies born to the mothers who smoked weighed, on average, 0.40 pounds less than the babies of the non-smoking mothers.
Nearly half a pound. That is an alarming physiological deficit for a newborn. It seems like an open and shut case, right?
You would think so. But the danger of unpaired data is that we cannot strip away the variance like we did with the textbooks.
Oh, because human birth weight is influenced by so many things.
Exactly. Maternal age, genetics, diet, and 100 other biological factors. All of that variance is baked into the standard deviation of both of those independent groups.
Right.
So when we run the hypothesis test to see if that 0.40 pound difference is statistically significant, the sheer volume of that biological noise artificially inflates the standard error.
And the math completely reflects that noise. When the t-score is calculated and mapped to the t-distribution, the resulting p-value comes back at 0.135.
Right.
That is far above the 0.05 threshold. So the strict rules of inference leave us with literally no choice but to fail to reject the null hypothesis.
Yep.
Mathematically, based purely on this specific sample of 150 births, there is insufficient evidence to conclude that smoking lowers birth weight.
Which is crazy to hear.
It feels like a glitch in the matrix. I mean, decades of robust medical science have proven beyond any doubt that smoking severely stunts fetal development. Yet, this rigorously applied mathematical formula just looked at the data and shrugged.
Well, the formula didn't fail. It simply reached the limits of its resolution. This introduces the crucial phenomenon of a type 2 error.
A type 2 error.
Right. A type 2 error occurs when a genuine real-world difference exists between two populations, but your specific sample size is just too small to mathematically detect it through all that noise.
So the 0.40 pound effect was absolutely real, but with only 50 smoking mothers in the data set, the statistical power of the test was just too weak.
Exactly. The signal was completely swallowed by the natural variance of human biology.
This raises an important point.
This raises an important question, actually, about how we interpret the phrase, fail to reject the null hypothesis. Failing to prove a difference is radically different from proving that no difference exists.
That is such a vital distinction, which brings us full circle to that chilling 1971 quote from the Philip Morris executive.
Right, back to the beginning.
When he went on television and claimed that the smaller babies of smokers were just as healthy, he was basically weaponizing the concept of the type 2 error.
He absolutely was.
The textbook fact checks this directly, noting that these smaller babies are definitely not as healthy, but it impartially demonstrates how he was taking the inability of small, noisy, unpaired studies to reach statistical significance, and he was deliberately spinning that absence of evidence into a corporate defense of safety.
To combat that spin, you really must understand the relationship between sample size and standard error. If you were to expand that North Carolina study from 150 births to, say, 15,000 births, the natural biological noise begins to cancel itself out.
Because you have so much more data.
Right. The standard error plummets. And suddenly, that exact same 0.40 pound difference generates a microscopic p-value, rendering the harm of smoking mathematically undeniable. The size of your lens dictates the clarity of the truth you can observe.
That realization right there is the ultimate takeaway of our journey through Chapter 7. Inference for numerical data isn't just about plugging variables into a calculator. It is an entire philosophy of rigorously managing our own uncertainty.
Well said.
We learned how the t-distribution mathematically thickens its tails to protect us from the false confidence of estimating standard deviation from a small sample.
And we leverage that mathematical safety net to pinpoint dangerous mercury concentrations in Japanese dolphins and to prove that the slowing finish times of those cherry blossom runners weren't just a fluke.
We discovered how pairing data strips away massive variance to reveal the true cost of textbooks at UCLA, and we confronted the grim reality of unpaired data, where the biological noise of a small sample can result in a type 2 error that literally masks genuine harm.
It's a lot to wrap our heads around.
It is. So for you, listening right now, dealing with data every single day, how do you operationalize this? When you are handed a report that boldly claims a new strategy is statistically significant or a new product shows no harmful side effects, you can no longer just accept the headline.
You have to interrogate the mechanics behind it.
Yeah.
How small was the sample? And did they properly apply the t-distribution to account for it? Did they pair the data to eliminate underlying variance? Or are they comparing fundamentally different independent groups?
Right.
And most importantly, if they claim an effect doesn't exist, is it possible their sample was simply too small to detect it?
You really have to ask if they are using a fine point pen to draw a map based on a blurry rumor. But I want to leave you with one final structural provocation before we go.
Oh, lay it on us.
All the rigorous mechanics we explored today, the strict condition checks, the thick tails, the obsession with degrees of freedom, they were engineered for an era where gathering data was incredibly expensive and samples were inherently small.
That's very true.
Today, we operate in the era of big data. Tech companies and researchers routinely pull data sets where the sample size is literally in the millions.
And when your sample size is 1 million, the degrees of freedom are essentially infinite. The t-distribution vanishes entirely, collapsing perfectly into a standard normal curve.
The math changes.
Yeah, the standard error drops so incredibly low that even a completely meaningless fraction of a difference generates a highly significant p-value.
That is the modern trap. In an era where the sheer volume of data makes achieving statistical significance virtually effortless, are we abandoning the rigorous discipline that the t-distribution forced upon us?
That's a scary...
When we have millions of data points, it is just so easy to stop checking for those extreme outliers that warp our reality. It is easy to confuse statistical significance with practical, real-world impact. Even if you have 1 billion data points, if you stop critically evaluating the shape of your distribution and the variance within your groups, your beautifully plotted normal curve is still going to lie to you.
It sure is.
Keep your lens focused, everyone. Thanks for taking the deep dive with us.